Which 101?
Yeah.
Is it science?
Yeah.
Most of the classes, like genetics and then developmental psych, like
Friends, I want to address two amazing questions that came from over here. And I want to get them on camera because they're really worth hearing. JC, ask me your first question, which was fantastic.
So I asked if every statistic has confidence interval.
Good. You almost said margin of error. And that's also correct. A margin of error is essentially tied inherently to a confidence interval. Because this is why I taught you guys margins of error in 243. I didn't teach you what confidence intervals were, but I taught you to look for margins of error in studies. Because those folks that did not make the journey to 244 still should be able to process what a margin of error is in the world. Now the answer is yes, every statistic has to have a margin of error. Because there is always an element of unknown in the measurement you've got. You know you didn't get the a parameter has no margin of error because there is no error. You know you have everything in front of you. There's no margin of error. Margins of error are tied to samples. JC's next question, which was equally good, was, why have I never seen them before? That's what frustrates the hell out of me in the news. The news very rarely publishes margins of error. They say things, remember the joking one I gave you, that Congress is now less popular than syphilis. I mentioned that one to you in 243. Because the syphilis infection rate is something like 10%, and Congress's approval rating was something like 9%. So 9% is less than 10. Except it's not less than 10. The 10% most likely has a margin, because we haven't tested everybody for syphilis. Never tested me. We haven't tested everybody, which means we have some unknowns. We have some plus or minuses on there. And the 9% from their sample of the approval rate also has a plus or minus, probably 3%. So unless the margin of error is so tiny that 9 and 10 look kind of like this, then they're essentially indistinguishable. Speaking of which, I want to get your question too, Renee, but let's answer Sarah's point with JC's. I think this is actually good too, right? Because I want to answer your P hat and P double hat question. The idea of a margin of error, Madeline mentioned that 5.6% seems kind of wide. Okay, I love that. We'll deal with that momentarily. But the reason I like this an awful lot is, as Sarah pointed out, you can draw these and get a visual of what they actually look like, which is fantastic. So let's do that with this one. Let's put a number line down here. Okay, and this is just percentage of heads. And up there, let's slap, I mean, we've got to go from 40 to essentially 50. So I'll start down here at 35%. Maybe go to 40%, 45%, 50%, 55%. And you can go further if you want to. I mean, essentially, it's going to go down to 0 and up to 100. And you're happy. But that's essentially enough. That's enough to see. Our sample resulted in a margin of error of 5.6% centered on 45.8%, which means that we went all the way down to 40.1 up to 51.5, which is going to be somewhere like in here, I think. Got used to that yet. That range of values is essentially the same thing that's in parentheses in this green box over here. Now the reason I like this, having it drawn out, I think it's fantastic to draw them out, and here's why. Here's why. We still don't know what the exact percentage is for spinning heads. Can we say that it's any different than flipping a coin with this confidence interval? And this is very often what you do with confidence intervals. Because we went into that experiment on Wednesday and we said, okay, it's like flipping a coin. It's probably 50%. Is this evidence that it's any different than 50%? What do you think? What do you think? Have we disproven 50%? For example, could it arguably be not 50%? The whole thing shifted left, right? I mean, it's not centered on 50. But what's true? Well, go with 310 trials, one experiment. I like that. Good. We'll come back to that, JC. Thank you. Say that again. There's the problem is 50% is in the interval, isn't it? Now, we do not know where little p is. Little p is the actual percentage you flip heads. The actual one that you flip heads. The actual one. We know it's in here somewhere. That's all we know, is that it's in there somewhere. So the problem is 50% is still in the interval, which means we haven't disproven 50. Even though I know it's tempting to say that the entire interval, except for a smidge, is left of 50. It seems like it's less than 50. You can't say that because 50's in there. Matt, what's on your mind?
I love that you can see I'm thinking.
Uh-huh.
Well, what I'm thinking is that the 50%, the coin flip would also have a margin of error, and so there would be two, actually, that you would be comparing.
That's an awesome statement. Here's my retort for it. Not because I don't like it, I think it's fantastic. And that would actually drive home the point, you can't distinguish them even better. But my argument is that there is no margin of error on the coin flip, because we can treat that classically. There's two possibilities, heads or tails.
Okay.
There is no error on it because we've stopped it.
Okay.
We've stopped it in the air and dropped it. That's one argument. The second argument is an article I read about 2 years ago that the title of the article was great. Guess what? Flipping heads isn't 50-50. I'm like, what?
Yeah, it's like 51-49.
But it's not. And here's the deal. Here's the deal. This dude had built a flipper, like an actual flipper that flipped a coin the exact same way every single time. The exact same way every single time. So essentially, he was taking any butterfly effect kind of stuff out of the experiment. When I had you guys spinning coins, you guys were spinning coins on the desk, they were bouncing on the little groove, you were bouncing on the floor. I mean, there's all kinds of little variables we weren't marking. He built an experiment to perfectly flip coins. He didn't want to assume it was 50-50. He ended up being something like 50.1 to 49.9 or something like that. But he did like 5,000 trials, which means the margin of error shrank down, but there's still a small margin of error. But at the end, he admitted that even his coin flipper had slight variations in design he couldn't account for. So he says, I have no reason to think it's not 50-50. So in other words, I'm not treating it experimentally. I'm saying if you flip a coin, there's two outcomes. Heads, tails, 50% of the time you're going to get one. So there's no need to have a margin of error on that. There is definitely a need to have a margin of error on spinning a coin, though, because we have no idea what's going on there. We're not stopping it. It's stopping itself. And because it's stopping itself, that's essentially what we're measuring is what's going on when it stops itself. Is that fair?
Uh-huh.
Good. Renee, ask me that question you asked me before, because it ties into what we're about going to next, I think. You felt bad about the outliers, right?
What if you... Oh, I don't...
This was good. It was good.
What if you don't catch the outliers?
Yes, the concern was with the outliers as well as the non-outliers. And it ties back to what Lauren said about precision, about how the curve seems too wide and you miss the outliers. Outliers are going to happen. They're going to happen. Every once in a while, you're going to get a data set that is just completely off the mark. Now, that has to happen. I mean, it's a bell curve. It's got tails, and you're going to land in those tails. When Max was at OMSI dropping the balls into the thing, every once in a while the balls landed at the ends. Not as much as they landed in the middle, but they did land on the ends. The trick is you can't focus on the outliers. But the outliers, just like the rest of the data, when the curves smush in, smush in. So you're going to miss them with the same percentage of 5%. Or you're going to catch the outliers with the same percentage of 5%. Go ahead. Mm-hmm.
But last term you said that sometimes the outliers, like, mean something. Like...
Oh, sure. Like, for example, suppose we're trying to see if a certain drug has headaches causes headaches at a higher rate than a drug that's already on the market. This happens all the time. How many times have you seen commercials for new drugs? Right? Yeah, right. Why do new drugs come out? Well, the cheap and easy answer is pharmaceutical companies make millions of dollars a year on them. But the more noble answer is we create better acting drugs with fewer side effects. So we're trying to see if the side effects are different. So pretend, for example, can I draw a quick diagram? I want to come back to this in this class, but here's a quick diagram to answer your question. Suppose that, based on studies that have been done about an existing medication, this is the average percent of headaches of the new medication. Okay. So, or excuse me, of the old medication, when we're already using. So we know that 10% of people or 5% experience headaches as a side effect. So Pfizer goes into the lab and tries to make a new drug that treats the same condition, but it wants to knock the headache rate down as a side effect. It wants to get it down like at 4 or 3 or 2% or something like that. So they go out and do a study, and they get one data point. Yeah, they get one data point, and they build a confidence interval on that data point, and it looks like that. Okay, that is definitely an outlier on that curve. So there's one of two explanations. Either we just got lucky and got one of the outliers, which is a possibility, but that's only going to happen 5% of the time, right?
Mm-hmm.
Or a more likely explanation
is that curve is
is there's another curve for the new medication. There's a different curve. So yeah, we want to catch outliers sometimes, and they are meaningful for stuff like that. And that's what the whole fact, like 8 weeks of this course is about. I promise you that. Yeah, good question. Very, very good. A little, I don't want to get into the mathematics of that yet, because I actually created a section to go between this and that I think will drive the point home even better. But that's exactly, they are meaningful. Sometimes they're just data errors, but sometimes they actually tell us something. Something's changed. This is cool. Something's different. Headaches are now better on average than they were. Good? Fair? Good. JC, go.
Okay, so if you catch an outlier, but how do you, because we're not supposed to know it.
Mm-hmm.
So you do more, you just make the contrast.
Here's the problem. No, this is great. This is great. This is great. Remember, you don't see any of this stuff.
Yeah, that's throwing me off.
You get that.
Yeah.
So all you know is the reported percentages that have come in, historically, reported percentages have come in, reported, it's hovering around 9%. This is what people have reported headaches using the medicine. It's hovering around 9%, 9%, 9%, 9%, and then your study comes back and it looks like this. The conclusion, therefore, is your new drug has less headaches. You could be wrong. They could have exactly the same number of headaches, and you just caught an outlier from this curve.
So
Or it could...
You say that when you...
No, well, you say you're 95% confident. And that admits that you might have a 5% chance of what's called a type 1 error, which means you missed it just by randomness. Okay, hold that thought. I got a graphic that hold that thought too bad. I want to hear it. I do want to hear it. Watch this, JC. I think this might clear it up for you. And then this might also address Renee's question even more. Here are 8 years worth of penny spin data. Brandon, if you don't mind, thank you, sir. 8 years worth of penny spin data. Yes, I collect this kind of stuff. Here's you guys, right here. There's your interval. I've broken up, it's kind of hard to see. You'll see it a little bit higher. This is 0%, 25%, 50%, 75%, and 100%. So we did the same thing Sarah asked us to do up here, except we've done it, stacked on top of each other. What do you notice in very, very many of the intervals? Many of them are below 50%, aren't they?
I already know what's coming up.
You do?
Because I know somebody that was in your class.
Oh, Tamara! She did this experiment too. She's back here, I believe. I think she's here. Yeah. So, take a look at all the intervals though. Notice how some of them are wider and some are narrower?
Yeah.
Why are some wider and some narrower?
Because there were some outliers. There was somebody that got 0.
There's an even easier reason than that.
Your sample set.
Because believe it or not, every single set of data that comes in, I had you guys collect the data, I said, how many, you got 2 heads, 3 heads, 4 heads, 5. They almost look identical almost every single time. But the difference is, somebody just said it.
Your sample size.
These are the sample sizes right here. Notice, when the sample sizes are larger, the intervals are narrower. When they're smaller, they're wider. Did you catch that? When sample size, now it doesn't line up exactly perfectly, you gotta have to make your mind kind of, you have to have your eyes kind of track them left to right. I try to make them scale the right way. When the sample sizes are larger, the margin of error shrinks down, doesn't it? And it has to, doesn't it? Doesn't it have to shrink down, friends? It has to shrink down, because if it doesn't shrink down, that means it either stays the same or it gets larger. But that defeats the point of the central limit theorem. It would be disproven by that. So you guys, and actually the past 3 classes that did the experiment couldn't disprove 50%. But look at the classes that could. And I love this, because I don't know what the friggin' answer is either. I have no idea what the percentage of time you get heads is. But I do know this. If I take all of the class's data completely and put it all together, on average, we have gotten 44% heads. And then the margin of error, when I use all the trials together, shrinks down to this. Lauren, here's your precision. Here's your precision. That margin of error is somewhere around 1% or less. Now, does this look to me like it's less than 50%?
Yes.
Hell yeah, it does. Way less than 50, like 5% less.
I'd say one of the sides of the coin weighs more than the other side of the coin.
That's the best explanation I've heard. The heads is heavier than the tails on a penny, which means inertia kicks in once it starts spinning, and an object that stays in motion, or an object in motion tends to stay in motion, and it's going to keep spinning where the tails gives up. Tails is less massive, therefore it has less inertia, therefore it gives up, but the heads keep spinning and pulls itself right down. meaning you get more tails than heads on average. Only explanation I've got. I have nothing else, Sarah.
Well, I kind of did some picture ones, and I noticed that if I did it left, if I spin it with
Yeah.
my left hand, I got always
Mhm.
tails. But if I spin it
Interesting.
with the
How
other
many trials did you do? Out of curiosity.
oh, only 30. Not
30?
a lot, but it was
Interesting
every
check.
single time when I did my left way. It was
Because on average, people are right-handed, so they
Yeah.
flick with their right.
so I wonder how many percentage of the class like if
We could control for that, couldn't we?
Yeah.
I could control for that by making you spin with your dominant hand, head facing outward or something like that. That's a variable. Remember how I mentioned the experiment was loaded with variables I didn't control for? And that would be one of them. If I made you flip with your dominant hand, or had you all spin the same way, for example with a flick, as opposed to a spin, that might be different. I don't think so though, and here's why I think it might just be random happening. My physics, and I don't know much physics anymore, but what I remember from physics, once that thing starts spinning, the physics kicks in. It doesn't matter how it got there, but now it's spinning. Kind of like it doesn't matter how Earth got into the orbit it's in, it's just there now. We have all these theories for how the Earth was created. It's there, it's spinning, it's going, you know, and I'm kind of thinking of it that way too. We could control for it though to see if there's any difference. I don't know if there would be.
Maybe you should have everybody spin it with their opposite hand.
That's true too. I don't know.
We
I
should
mean, there's
do
all
it
kinds.
first.
This is why you take research methods classes. And this is also why we don't care about spinning pennies too much. Yes, Laura, except for doing this kind of mathematics. Go.
But the whole 8 years of data thing would kick out the how you spin it because it would narrow it off.
You think so? I think so.
Because
I agree.
You're gonna have plenty of people with left hands.
I would think it become exactly. It's the Sports Illustrated cover thing. It's regression to the mean. So I agree with you, Laura. I totally agree with that statement that it's eventually going to get down to the point where it doesn't matter anymore. I agree. Cool? Any other? JC, go, no, go.
Okay, you might have already answered this before, but why is it okay to have all these different sample sizes and combine them together?
Mathematically, it's okay because that's a great question. I haven't answered that yet. Why is it okay just to do? Because essentially, what I did was I added up all of these and called those
It
n.
makes sense mathematically.
Oh, that's the only reason. Because this is based in mathematics, and I know if you have me in 243, I tried to make statistics as little as mathematics as possible, but mathematics underlies all of it. It's number of successes over number of trials. Assuming all the trials were done well, then therefore I can just add all these up and just treat it as one big experiment. It's replicating the study. I'm essentially taking a weighted average of the results by doing it that way. It's a weighted average again. So I mean, not to play the math card, but mathematically it says I can. And because the sample size is now somewhere around, I don't know, 8,000 or something, or 10,000, we get a margin of error that essentially shrinks down to zero.
This is what happens with like the drugs and all of that.
Exactly. Those drug trials have thousands and thousands and thousands of trials. Michael, go.
They're all sampling the same thing, so you can
Assuming that I didn't have any goofy outlier data set anywhere. They're all sampling the same thing, so they can be true. Replicating the study. Have you heard of that? The idea of study replication? Seeing, because that way you can see if did you get an outlier. Well, 4 studies that tested the same thing in the same way all got the same results. So the chance of all of them being an outlier is 0.05 to the 4th power, which is essentially 0. It's like the chance of all the RAID disks at COCC failing simultaneously. It's not going to happen, right? It's not going to happen because it's too hard for it to happen. If that's a good answer, that's a good answer. It's a great question. Cool?
Yeah.
Now that's fantastic, except for this calculation over here, which sucks. I don't want you doing this crap by hand. It's too easy to screw it up by hand. So, grab your TIs, and let's make sure we know how to crunch this with the technology. Brent, leave that light off, actually.
You still got mine.